You've arrived at another Draft Science video production. This one on the subject of gravity. The update. I had previously made a statement about gravity, about equilibrium, and as an explanation for, how more stuff could go in than goes out, Well, anyway, and it's rubbish. So I'll explain that. And I'll explain the real reason there's gravity. A better reason, better explanation. Just getting to it is sometimes difficult. So anyway, the premise, which you need to understand before, if this is a first video, watch the other videos in this subject playlist, which this one will go into as the video on gravity, because this is the updated, most current, best video. Anyway, will be, eventually. It's going to get better. So, gravity, you have to understand first that there are two kinds of force. There's the electron force, the proton force, the plus force, the minus force. And we're really just talking about what happens to matter bits, bits of electrons or protons. That's what a matter has to be made of, is electrons and protons. And those are the plus and the minus of the red and the black, the elements. And that's all there really are. So it's 2 plus 2 plus 2 physics. There's two kinds of force, there's two kinds of matter, and there's two kinds of interactions. So anyway, for the purpose of gravity, there's no polarity. That is, it's like a piece of iron. When it's not magnetized, all the little magnets inside, all the atoms, are pointed in every possible direction. They're randomized. And therefore they cancel each other out as magnets. So there's no magnetic effect. And then when they're lined up, their magnetic effect arises out of the fact that they start segregating these two forces. They push one force one way and the other force the other way, and you end up with a magnet. And that's a perfectly good explanation of the phenomenon of magnetism. Alright, so for the purpose of gravity, we don't have to worry about polarity because it's canceled out. It's randomized. There's only a tiny magnetic field around the Earth and the Sun, and it just doesn't play any significant role in the function of the gravitational attraction. Now, there's a thing called the gravitational constant, the big G, that's in the equation. So it's G times mass 1 plus mass 2 divided by r squared. And the G, got to wonder about a constant that is in the origin of the mechanism, in a sense, and why it even exists. I just noticed my phone isn't charging. I have to fix that. You don't really have to, because nobody worth talking to calls most of the... Anyway, alright, so, and it's this preposterously small number. So, because they were... Well, let's go through it. So the idea of gravity, from a rational perspective, so just ignore all this stupid bent space crap, and let's come up with a real explanation for the effect that causes two objects to move towards each other. Now, my simple alternative explanation is that there's, as pointed out before, there's all this force from the external universe, like the cosmic background radiation. It just is. Okay, it's there, and it's coming from all directions, which I obviously can't draw, so it comes from all directions, the 3 dimensions. And it surrounds any single object. So obviously if this object was alone in space, it would just circle it, and for every location in space there would be stuff that is going to pass through that location. So the little bit of radiation, the cosmic ray, the microwave, whatever photon you want to pick, whatever variety of thing moving the speed of light, or more precisely the speed of force, will intersect with every certain location in space. There's a certain number of photons that are going to pass through that space, and so essentially everything is the target. And so when you put two things in proximity to each other in a field like that, one that's going from all directions, they end up blocking, essentially, shadowing each other from the force. And you could understand that if this one doesn't let a force go through it, the force can't hit here. If it can't hit here, then there'll be more force over here and less force here. And obviously if these forces were pushes, you can understand that this object would have to move towards the other object. Now this is basically the diagram of Mach gravity. It works as gravity. That's why they call it Mach gravity, is because this simple explanation does explain gravity. Now it has other problems that they think makes it not work, but obviously those problems can be understood as not being problems, as being part of the truth, and perfectly consistent with other things that we know to be true about material objects. So you can just basically understand it as a shadow effect. Now, as I've explained, this is a nuclear force, gravity. It affects every little bit inside of something, directly or indirectly. By affecting one little particle inside, you affect all the other particles because you move them closer together, and the charges don't like moving, like charges don't like being moved closer together, therefore they repel each other, and the force is transferred between all the little bits inside of the big bit. So it's essentially, you could break anything into little pieces and gravity would work identically. So if I took the Earth right now and just separate all the little bits, it would still orbit the sun. All the little bits would still be doing what the big Earth is doing. These are just preliminary facts, just to make sure people don't trip on the obvious, or what's already been established. So it's a nuclear force, so it should never be treated as some kind of gravity only happens to big things and all this kind of crap. It really does happen to the little bits. It really should be understood that they have to make quantum mechanics and gravity. They do have to fit those two together, because quantum mechanics is about the movement of photons and electrons, specifically the interactions, and electrons are moved by gravity, so this is all part of the same subject. Alright, so in previous theory my argument is that, so obviously over a period of time, what's going to happen is some bits are moving one way and other bits inside are moving the opposite way, and these bits are still being accelerated. So you can understand that the little bits are still being accelerated towards the density of the object, in the sense the center of its gravity. So when we're sitting here on Earth, we do dent cushions, we dent floors, we dent things because we're still accelerating. And our acceleration is met with what is an opposite reaction, a pressure back. Okay, and so we're really just bouncing in gravity. But the pressure is real. So there's high pressure inside a gravitational, a big one. There'll be a high pressure. So the bigger you are, the higher that pressure is going to be, because you have more and more stuff that's just constantly trying to accelerate towards your center. And it's being met by other stuff doing the opposite. So there's these collisions, and collisions are essentially heat. So it heats up. So you can understand that anything that's big gravitationally has a lot of elements to it. It's going to have a lot of conflict, a lot of elements swirling about, essentially. So you can also understand hitting each other as missing each other, but ending up in some sort of pattern, fluid. So it is understood that the center of the Earth is hot. The only thing that's heating the center of the Earth is gravity. We know the sunlight isn't getting to the center of the Earth, so clearly it's gravity that's heating the center of the Earth and making it molten. And it's pressure. It's just this constant pushing in the direction of the absence of the force hitting things in the opposite direction because of the shadowing effects. Alright. But it's also happening interior, so you got to think of it as each gravitational body has gravity happening inside of it. So this object here is shadowing this object here, shadowing this object here. So these that are moving this way are absorbing force that would have hit these over here. Now it doesn't hit those, and so they move in. And then when they move in, they absorb a force, a little bit of an arrow, and this arrow doesn't get over here, and so then they move in there because there's a constant exchange happening. So you sort of have to understand a little bit about the mechanics of the electron and the proton, which is the force enters, it reflects, but it changes the momentum of the electron. And so the electron is essentially carrying the force. I've explained this in a lot more detail in other videos, so I don't really want to spend too much time on it here. But it sort of is important, because to understand the electron, you have to understand that the electron is constantly moving in a direction. See, it has an odd number of places to hold arrows. So when an arrow goes in, an arrow has to come out. So if these were going this way, and these two are going this way, as its net product will be in that direction, 3 to 2. If I just change one of these arrows, you can see it's 3 to 2 in the opposite direction. But it always has to be in one direction or the other. And it's doing that in all 3 dimensions. So the electrons are likely moving when you hit them. You don't hit a stationary electron. You always hit an electron that's going, say it's going this way, okay? You hit it with a force this way. Well, it's also coming out of the board, so it's going a little this way. And so then when you hit it, you're just adding another velocity vector to its net vector. So you have to understand that the electron or the proton has a net vector, a net direction that it moves in, that's based on what forces it has previously absorbed. That is, what kind of rower, say these little force bits were thought of as rowers, what rower jumped in the boat and what rower left the boat. And it's always an opposite rower who jumps out from the one that jumps in. And that's a pretty simple diagram. So anyway, so that's a way of understanding the thermal problem. So what you could understand is that as something is becoming gravitational, that is collecting parts, it's getting hotter and hotter, and heat is essentially a collection of force. So you're collecting a lot of density of interaction inside of a gravitational body, which means you have stuff all the time absorbing force in one direction and absorbing force in the opposite direction. Alright, I think I'll redraw this for clarity. Alright, so first think of it without there being another interactor in the story. So you just have an object, a big object. You understand that every little bit is still gravitationally absorbing force, so it's still accelerating all the time. And accelerating requires the new absorption of a force. To keep moving, it has to keep absorbing something to keep moving. But anyway, so it has it's absorbing energy in all these directions all the time. All right, and so the question would be, well, where does that energy go? So I had made the argument previously, and it's just wrong, that the energy comes in little discrete soldiers, and that it somehow that it leaves in bigger clumps of matter with a momentum, and therefore you could understand that you're wasting your energy because there's 100 energies, you could say, in this clump, and you're coming against a field, you know, of individuals. And so if you send 100, you'll only kill very few of these opposing forces, and you'll leave a bunch of them free to attack you, so to speak. A sensible mechanism. Maybe it has some use for some other purpose, but it's not an explanation for gravity, because gravity, clumps wouldn't matter. So if it comes out in clumps and hits this, if some clump hits this planet, it's going to be the same. All of its force will be released, and all of its energy will be realized. So there won't be any difference between whether the energy comes in a big clump or the energy comes in a bunch of little soldiers. It'll be the same difference to something like the size of the Earth. So it doesn't provide an explanation for the equilibrium problem, which is once the Earth heats up, it gets a temperature then it can't keep absorbing more than it releases. Somewhere it's got to go out. And it does. And it's just irrelevant though. See, the real trick is if I put something over here, and you understand that this force is an absorption, that is, these bits to move have to absorb a force coming from the external world, okay, you can sort of understand that the one that absorbs this arrow was heading for this. It got absorbed by this object, and a little bit inside moved this way, giving it a bias in this direction to move. So this absorption, that would be felt by this one because it didn't get hit by the arrow. Therefore, it's going to move in this direction because there's going to be less stuff hitting it this way than this way, right? I mean, and so you can understand it moves forward. Now, what happens when this force gets absorbed going this way? Well, it's totally irrelevant to this. This one couldn't care. This one's running away from this one. It can't possibly hit it. It wasn't going to hit it. So whether this one goes here, this way, or whether it goes this way, or whether it goes that way, can't mean anything to this one. It's just totally irrelevant, any change. So the only thing that matters to this is what's hitting its face here. And this wasn't going to hit its face. So when this gets absorbed, that is, this object moves in the other direction, when it absorbs energy in the other direction, it's not going to be felt by this. So the equilibrium is in the very fact that we're only going to notice the stuff that didn't get to us. We're not going to notice stuff that would never have hit us and isn't going to hit us. So all of the absorptions that happen in this, that have a component, just a component in this direction, we're not going to feel, this object won't feel any of that. So all of that absorption and all of that, anything released in that direction, it will likewise not be felt. And so that's one way of understanding the equilibrium. Problem is solved by the fact that the only thing that matters is the absorption this way. The absorptions this way won't compensate here. And so all of this thing feels is the absorption of the energy that would have hit it. Okay. Alright, so going a step further. So to understand, there's this thing called the gravitational constant. Alright, and so it's this preposterously small number. 10 zeros, 6, points, 10 zeros, blah, 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 blah. Might as well draw them just for effect. That's what, 9, 10, 6. Okay, so very small number. And you're just saying, why is that? There's probably a reason for it. Why didn't they just say 1 and then just change what a Newton was? Obviously there's some reason why they think this matters, because they want to put it into meters and then seconds squared, and what else? There's a time component, the distance component, and velocity? No, I don't think there's a velocity component, but it doesn't matter anyway. So it's some complex thing in Newton, but anyway, it doesn't really matter. Point is why is this number so small? Alright, and the answer would be is in that fact that the electron is already moving in three, it's moving in the 3 dimensions, but it's moving in the sub-dimension. So it's either going forward or back. So if it's not going back, then that's a 0. It's either going left or it's going right. So that's a 0 over there for left. And it's either going in, which we'll say it is, or it's going out. But in those 3 dimensions, it has a vector, and so its net motion will be the product of those 3 motions. Will be some product direction. So every time when an electron is absorbing the force, you sort of have to understand that it's already moving some other direction. So inside the object. There's all this stuff moving. So your electron could be moving this way as one of its components. It has a component in that direction. You're hitting it with a force this way. So you're going to change that direction to some other, direction that retains both components. Will now be added into this new direction. And so when absorption happens, the absorption is essentially happening in the sense that the gravity isn't always leaving directly between the two objects. So the shadow this one creates, it absorbs the force going this way, but the effect of the force is to change something moving this way, or this way, or this way, or this way, or this way. So in a sense, the gravity is spread over the entire subdimension. So there's 3 dimensions, and you could say 6 subdimensions, but you have, this would be the forward, this side would be the back. And so over the entire forward direction is where the response to this absorption is released. So this bit of force gets absorbed and it's released over this entire, the two sides of that face, so the half of the sphere. And that's what this number represents in terms of a diminishment of the force. So if it was if it responded by creating an equal and opposite reaction that went directly to this object, then this number would be 1. But because it's spread over the entire sphere, see, this number has the appearance, the 6 is sort of a, it's almost a reciprocal of pi. The 3.1, you add 6, you're getting to 9.1, and then you add the 0.4, and so you're getting to 9.5. So you're getting close to 1 in terms of it being reciprocal or something to do with spherical numbers, pi-like numbers, circles. Well, anyway, that might just be a coincidence, but I'm just pointing out. So anyway, so the absorption is for this gets absorbed, all right, but what gets radiated as a consequence of actual movement of this object, that is, where it senses the difference, can be in any one of these directions. And so the counter absorption, if you want to call it that, will be in any one of the opposite side faces, however you want to describe it, of the object. So the point is that that's why gravity is described as a weak force, because unlike charge, when 2 charged objects are interacting, all of the significant interactions are straight lines between them, and this stuff doesn't mean anything to their interaction. Nothing gets moved because these are elemental particles, and they themselves don't do the inside of them is no jiggle. Yes, they move, but their movement doesn't change the direction of a force because they are directly interacting with the force. Yeah, I think that is okay the way I said that, but it doesn't really matter. The point is to understand is that the gravity is returned to space. The force that's absorbed is returned in any one of these directions. So if this is absorbed, so if you absorb this, essentially what the argument is what you're going to eventually, so this is the input that goes into the system to heat it, and the output can be in any one of these vectors for that individual bit. And so the only one that's going to matter to this is obviously one that is actually this direction. So that's the 0.6. The small number 6 means that this is 0.0006 of the time, okay, you'll have the force will actually get to this object, the absence of force, if you want to call it that. The realization of the absence will only affect this object 0.0006% of the time. The rest of the time it's missing it. It's going somewhere else as a change in the field. So that means that the gravity here and 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 here is all the same. And since the same exact thing is happening on the opposite side of the universe, so to speak, the gravity over here is the same, and the gravity over here is the same, and the gravity here is the same, and so that's why gravity is r squared. So in a sense, you can understand that the first principle, all right, is the fact that it's spherical. So if you take the formula, force equals G, all right, and then mass 1, mass 2 divided by r squared. I hate doing math, but anyway, I'm doing a little. So the G part is the fact that this goes in and this comes out. Okay, so as an effect, I'm not saying the force doesn't come out. This actually represents an absorption. This gets absorbed, and this is, the absence, what's felt as an absence in space. But anyway, for the purpose of understanding, so the G part is the fact that the sphere is going to throw this vector. So each time it shoots a photon, it'll shoot it at one of these locations, and over time it'll shoot an equal number here, as here, as here, as here, as all these locations. And so that's the G part, is that you took something that was this and you broke it into all these vectors. So something that had one vector, you broke into all of these vectors. So that's the G part. And the r squared part is that when you take these lines and bring them out and then you square it, that is, you recognize it's happening in 2 dimensions, all right, that it's spreading in both directions. So it's not only spreading this way and this way, it's spreading that way and that way. And that's the r squared. So the r squared is just telling you that it's spreading. These arrows are getting further apart from each other. The ends of the arrows are getting further apart from each other in 2 directions, this way and this way, and you could say this way and this way, if you were to make the square. No, that's not a very good drawing of the square, but anyway, you should be able to get the drift. It's moving both ways. It's spread. They're getting further apart this way, and they're moving further apart this way. So you can understand that they can be very far apart. So that's the r squared part. So that sort of explains this equation, explains this relationship. The first part is you're reducing the force's effect by spreading it over a half of a sphere, and then the force itself is spreading with distance at this r squared rate, and it's spreading both ways. Alright, I think that's okay. Alright, so the issues with Mach gravity were first that the idea of, you would have this fundamental problem would be that how can gravity work if this object is moving and gravity moves at the speed of light? By the time there was an interaction, that is, by the time this object knew that this object moved towards it, which means it absorbed a force here, it would have to wait to know, oh, the force didn't hit me, and it would take time for it to be affected by the force here and move towards this one, and then it would take time for this object to know, hey, that thing moved towards me, and by the time all that happened, this would be over here, and so whatever gravity would be created, it would be in the wrong location. Well, obviously this fixes that, understanding that the absorption here ends up being a radiation in all these directions, fixes the problem, because now the point 0.0000000000006 gravity does get here. So a g amount of gravity gets here, and a g amount of gravity gets here, and a g amount of gravity gets here. So, well, it doesn't go back. Well, it goes back there, but the opposite process. That's the gravity being created by the stuff on these surfaces. This going this way, this going this way. So the gravity's there before you get here, because it's this matter pushing this absorbing force to accelerate. I'm accelerating. I'm absorbing force. The guy in China is accelerating. He's absorbing force. The only one that affects somebody right here, above me, so if I put this above me, the only thing that affects him is the Chinaman. I'm not affecting him at all. Okay, the fact that I'm absorbing force isn't affecting the thing above me at all. It couldn't care less that I just absorbed a force going away from him, because that photon was leaving. It's like, it just can't matter, because that's a force going away from me. So it was only the forces that were coming at me that were getting interfered with that could matter to me. The forces that weren't going to me, that is the light going, say if I have a light bulb in the middle of an open field, the only light that can hit me are the photons move in the right direction, right? And something can block those. But nothing, the ones on the other side can't possibly affect me. They're going that way. They're going the wrong way to have any effect on me. So if somebody blocks those, I'm not going to notice. If those stop being made, I'm not going to notice. All right. I don't know how to better put it, but so it's this guy over here absorbing the force that affects this. This counter force, the equal but opposite, you could almost argue, event, is completely invisible to this object. He can't see this. He can't feel it. He can't sense it. The absorption or the movement this way can't mean anything. He can't sense it in any way whatsoever. It's only the movement towards him that he can sense, because that movement, okay, has built into it the fact that a force that was going the speed of light is now moving a much slower and won't get to me. And so now I can feel it. That's the real reason, is that when, even though there's an equal amount of motion in this inside the object, that is just as much stuff is moving this way as this way, the only part this one feels is the motion this way. That's the motion that absorbed a force that was going to hit this guy. The motion this way just couldn't matter to this object. He can't detect it as a problem. Yeah, so maybe that's enough. Let's see if I covered enough. So the pressure thing needs to be understood. There's always movement on the interior because the electrons are always moving. Electrons are always moving, which accounts for why the stuff leaves in the wrong direction. The electron is already moving this way. When I hit it with a force this way, it absorbs this force, but it doesn't go, when the absorption happens, this thing's changing the vector of the absorption. This is going to be another way to say that. And the force will end up getting radiated or leave in some other direction. So the absorption will seem like he absorbed this when, something going this way, when no, he absorbed this. It's just going to come out the wrong way. Let's see. Doesn't leave. It's going to be realized as an absence of force in some other direction. See, this electron had a direction it was going. Okay, this is a better way to say it. I got it. It's very simple, but again, there's lots of nuance to this, so you do have to really do it the right way. So the electron is moving in this direction, so it's going this way. Now, that means there was an implication. Where it was going now isn't going to feel the electron hitting it here. Okay, so anything that was going to be dependent on a force coming to hit it here, it's not going there anymore. Okay, because now I've changed it by having it absorb a force going this way. And so now it's going to impose a force going over here. It's what's going to get hit. This isn't going to get hit. And so this is going to be where the absence is. And so that's the point being made, is that the electron's already moving, which means you're changing what's going to get affected by the force that electron inevitably will make when it has to change its direction. The electron can't leave the gravitational body. So when it has a momentum and a direction, it's obviously going to change that direction. And in changing that direction, it emits a force. All right. And what's the point? And yes, the point is that where it was going, it didn't go. The force got affected. The bit of energy went somewhere else, and it didn't go to this location, so this location has less force in it. And again, we only feel what rocks don't hit us. We don't feel the ones that go somewhere else. So the only ones that affect us are the ones bent from hitting us. Whatever the right way to say that is. I think it's probably good enough. Alright, so I covered that. So gravity is a nuclear force. It affects the electrons. The whole drag argument again was used. Okay, so I've explained why gravity is spread, why an object, why the time thing doesn't matter. The fact that this thing's orbiting doesn't change the gravity, because the gravity is going to be the same in all these locations. Anything that has anything in this plane, okay, is going to have the gravity created by this object. The counter force at 0.000006, okay, is going to be the counter force is going to be realized, spread over all this area, and so the gravitational impact will be felt in all these locations. So it doesn't matter where the object moves, it's still going to have the same gravity. So it doesn't, the time thing doesn't matter. The fact that this is interacting with this and that they are actively changing each other's vectors, their net potential, their net movement, it doesn't matter that the locations change, because anything on this side will always be the same, and no matter where you are, the sides always exist, so it just can't matter. So there was some other last point I wanted to make. Similar point, added point. So so it's got to be understood. It's a nuclear force. The drag subject. So I explained why time doesn't matter. Drag, which is this argument that if the Earth has got a velocity, it's going to hit more stuff, more force going this way than force this way, going with it, which means it's going to slow down. Well, the fact is that that's what electrons do. So the Earth is made of atoms, so it's different than electrons and protons. And the fact is, experiments demonstrate that we can't make electrons and protons move with a velocity perpetually. If you throw one into space like a wrench, the electron will just lose its velocity. It'll slowly slow down. That'll happen to its velocity. It'll do this. It'll go to zero, semi-rapidly. So you have to keep pushing electrons. So whenever we shoot electrons in a gun of some kind, it's because we have a voltage across and we keep hitting it with force. And so we keep propelling the electron, keep maintaining its voltage against drag. So we've got to keep adding force to overcome the fact that there is drag. There is in fact drag for electrons and protons. Now, why atoms don't have drag, that is why you can throw a wrench in space and it'll keep moving, is a more complex argument that goes to the polarity argument, in the sense that you can have force interacting between electrons and protons where you can just keep pushing two objects because you get to change this direction for free. So if this was a proton and it was changing the vector of the force, and these were electrons that always reflected the force, you could understand if I had a ping pong ball and I could change its direction without any friction, that the ball would keep hitting these two objects in the same direction away, with a component in this direction. And so it's essentially a little engine. The ping pong ball would just keep hitting and hitting and hitting and hitting and keep propelling the electrons against any drag that might exist. So there's an explanation for how drag is overcome in big matter, okay, things with atoms, atomic nuclei. I mean, it's basically stated that the only thing that does travel, the smallest thing that you can make, that you can keep going in space, is something like a helium nucleus, which is something like a hydrogen atom. But anyway, because it has these necessary components of a neutron and an electron. But anyway, it has 2 electrons and 1 proton built into the structure. And so it's basically this little engine that could. So this is what overcomes drag. But there is drag for electrons and protons. They don't keep moving unless you keep forcing them to. You have to keep applying something for them to absorb to counteract the extra energy they're running into. Alright, so outside of the, I don't know what they call it, aberration problem, anyway, the problem of the force not being even, okay, I've explained that, and then there's the drag issue, and I've explained that. And so there really isn't an issue, and therefore Mach gravity can work. The idea of a particle gravity can work, and explain everything quite nicely. So, I guess we'll leave it at that. I don't know if I'm totally satisfied I did a great job, but it'll have to do till the next update. But the important stuff is there. Something that was going to hit you doesn't hit you. It's really important. You've got to understand that if there's something in the way, and it moves towards you, and it absorbed something to move towards you, that something didn't get to you, and that's why you're going to end up moving towards it. It's because there's less energy between you, and it's really that simple. That's gravity. So till the next time and such. Call it a video. Mostly. Come on. Strange. I don't know. Just the options menus just don't work very well on this computer.